folks, welcome back to 7.3. So last time we talked about what a vector is, we talked about addition and subtraction and scalar multiplication. And so I'd just like to talk a little bit about some properties about addition and scalar multiplication of vectors, okay? So one thing that you can count on is that if you do a plus b, it's going to be the same as b plus a. So the order of addition doesn't matter. And similarly, a plus b plus c is the same as a plus b plus c. Okay, so the addition, the order doesn't matter. Now, there is something called an additive identity, which means that if you have a vector and you add 0, you're going to get the same thing. And then there's something called an additive inverse, which means you take the vector and the opposite of that vector, and when you combine them together, you get 0. All right? So those are the properties that deal with addition. Now, for subtraction, or for multiplication rather, you can distribute this scalar m to 1 and 2 vectors. So the distributive property works just as well with our scalar multiplication. Similarly, if you have 2 scalar quantities, you can distribute them to your 1 vector. And like the order didn't matter for addition, the order doesn't matter for multiplication either. And with this a plus 0 as the additive identity, the 1 times a is the multiplicative identity. And we have our 0 vector, which means that any vector you take and you multiply by 0, you're going to get the 0 vector back out. Okay? So these are a lot of the same rules as you've experienced for regular addition and multiplication, just in the context of vectors. All right, so let's take a look at magnitude of a vector. So the magnitude of a vector, all right, the magnitude of a vector is the length of the vector and can be found using either the Pythagorean theorem or the distance formula. So just to refresh your memory, the Pythagorean theorem is a squared plus b squared equals c squared. And the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. All right. So let's take a look at example 5. We're going to draw a diagram for this vector. Okay, so we're going to go ahead and draw this vector, -3, 2. So that means I'm going to start at the origin. I'm going to go 3 to the left and 2 down. And I'm going to draw the vector that connects those two. All right, so this is my vector. Now, if I want to find out how long that vector is, then really what I'm saying is I've got a horizontal component of -3, and I've got a vertical component of, oh gosh, I did it upside down. So sorry. -3, 2, we're going up. Okay. Well, we still have the same horizontal piece, -3, and our vertical piece is 2. And so now it becomes a little bit more clear why we're using the Pythagorean theorem. Because really, to find the length of this vector, I need to find out how long the hypotenuse is. So I'm going to plug those numbers into my Pythagorean theorem and then calculate my hypotenuse. So -3 squared plus 2 squared equals c squared. I get 9 plus 4 equals c squared, or 11 equals c squared, or we can say that c equals, oh my gosh, not 11, 13, my goodness. 13 equals c squared, so c equals the square root of 13. All right, that is the magnitude of my vector. So if I want to say magnitude of the vector, the symbols we use are a double bar, the vector, and a double bar, and that equals square root of 13. Okay? Okay, so let's do the same thing for example number 6. So I'm going to draw this vector, but I'm going to draw the horizontal component in the pink and the vertical component in the green. Now I know these are pretty small, but I want to go from the origin. I'm going 4/5 to the right. And from the origin, I'm going 3/5 up. And my vector should start here and end here. And we can call that vector u. Now, if I want to find out the length of this vector, I can still use the same formula that I used to find the hypotenuse. It's just a smaller triangle, and it's got some fractions, but let's see how it works out. So, I'm going to take 4/5 and square it, plus 3/5 and square it equals the hypotenuse squared. So I get 16 over 25 plus 9 over 25 equals c squared. I get 25 over 25 equals c squared, or c equals 1. And so what that means is we wouldn't write c equals 1, we would write that if this is vector u, that the magnitude, double bars, of u equals 1. Now, anytime the magnitude of a vector equals 1, it is a special kind of vector called a unit vector. And we're going to talk about that in just a second. Okay, so magnitude of a vector is how long it is. You can use the Pythagorean theorem to find that hypotenuse. And then if it has a magnitude of 1 or a length of 1, it's a special type of vector called a unit vector. All right, let's take a look at the direction of a vector. Because we said earlier that vectors are special because they have direction and length. So it turns out that the horizontal component of the vector you can find from the magnitude times cosine. So let's take a look at where that comes from. So if I draw an XY grid and I draw a vector, okay, the magnitude of the vector is A inside the double bars. And this is my theta. I know the bottom part is what we call A sub 1, and the vertical part is what we call A sub 2. So if I use what I know about right triangles, I can say that cosine of theta equals A sub 1 over the magnitude of A. And if I multiply that magnitude of A to both sides, then I will get A sub 1 equals the magnitude of A cosine theta. So that's where that formula comes from. And we could do the same thing with the vertical component, except this, oh gosh, should be an A sub 2. So I know from this same diagram that sine of theta equals A sub 2 over the magnitude of A. And when I multiply both sides by the magnitude of A, I get this formula. All right, so that is how we can find the horizontal and vertical components of a vector. Now, what that means, if we put that all together, is that we can have something that looks like this. Okay? the magnitude of A times cosine theta I plus sine theta J. Now, we're going to talk about where this I and J come from in just a second, okay? But the I is not the same as the imaginary I, okay? So this I typically write like that without a tail, and then this J is a J. It's not really meant to be a script J, okay? But let's take a look at where that comes from. So, example 7. If the wind is blowing at 12 miles per hour in the direction of north 40 degrees west, express its velocity as a vector. So let's start by drawing a diagram here. So I've got this. Now north means it's blowing straight up, but then it blows an additional 40 degrees to the west. So that means that I have something like this, and that the angle altogether is 90 plus 40, or we could say that it's 130 degrees. And how long is that vector? Well, the magnitude of that vector is 12. So, how can I express this as a vector? Well, I can say that I have A equals, and we're going to use the magnitude of A cosine theta. That's going to be my horizontal component, and then magnitude of A sine theta, that's going to be my vertical component. So A equals, well, they told us the magnitude was 12, cosine of 130 degrees, and then it'll be 12 sine 130 degrees. And if you wanted to turn this into a decimal, you could say 12 cosine 130, and that would be about negative 7.713, and then 12 sine 130, and you would get that to be about 9.193. Okay? So that's how you express a vector, or express a vector direction, all right, with the direction. So I know when I look at this that my vector is going to be in quadrant 2. So we're going to go ahead and stop here for the second part of this video, and when we come back, we'll talk about the I and the J and that unit vector business.